In the last lecture, we have seen two important properties of the transition metal ion, and that is the complex formation ability of the first row transition metal ion, and also we have seen the coordination number and various geometries possessed by various coordination number. In this episode, I am going to tell you something colorful about the color of transition metal and their metal complexes. In beginning, let us start with one question: which aqueous transition metal ion is or are not colored? So, we have a zinc 2 plus, Cu plus 1, scandium 3 plus and titanium 4 plus. What do you think? Either all of them are colored or colorless? One more question to you: why some of the transition metal compounds are white? You have come across two different compound of a copper, cuprous chloride, that is CuCl, and cupric chloride, CuCl2, out of which the cuprous chloride CuCl is white in color. Why? So, if you look to the electronic configuration of CuCl, then in this the copper is 3d10 electronic configuration, and therefore, there is no space in the d orbital for electron to be promoted, and perhaps this is the reason why it looks white in color. In addition to the copper, that is cuprous chloride, some of the compound of zinc and scandium is also white in color. Suppose we have a compound of zinc or compound of scandium, we will have either 3d10 or 3d0 electronic configuration. So, one thing comes into our mind that the color may have some relation with the number of unpaired electron. As we have learned in magnetism that more number of unpaired electron and therefore, more paramagnetism is observed. So, does the same analogy is applied over here, that is to say, if we have a more unpaired electron, we have a colored, and if there is no unpaired electron, the compound will be colorless, as it was in magnetism, that is, if there is no unpaired electron, it was diamagnetic. To understand it, let us see few examples of some of the cations of first row transition metal ion. Here we have a titanium 4 plus or zinc 2 plus or cuprous ion. All of these in their electronic configuration have no unpaired electron, and therefore, they are colorless. However, if we have titanium in 3 plus electronic configuration, or we have a vanadium in 4 plus or copper in 2 plus, that is in cupric ion, then we have a one unpaired electron, and which will results to either purple, blue and different color. Let us go ahead. Let us take an example of a either vanadium 3 plus or nickel 2 plus ion, in which we have a two unpaired electron, giving them a green color to these cations. If we have chromium 3 plus or cobalt 2 plus, then we have a three unpaired electron, resulting into the violet, green or pink color to this metal ion. Further, the 4 unpaired electron in manganese 3 plus or Fe2 plus or chromium 2 plus results into different color, and at the end we have a manganese in 2 plus or iron in 3 plus electronic configuration will have 5 unpaired electron, giving them either pale pink or yellow color. So, is it the number of unpaired electron and the color is directly interrelated? You have also seen some of the metal salts of the transition metal ion in the laboratory. Some of them are colored and some of them are white. Say for example, you have a scandium oxide which is white in color, or you have a zinc sulphate which is white in color. You have vanadium sulphate. Vanadium sulphate is something bluish green in color. You have seen potassium ferricyanide, orangish in color. Manganese chloride, faint pink in color. Copper sulphate, all of you have seen strongly blue in color. So, what is the science behind the color of this solid compound of transition metal ion? Apart from the color of this compound in a solid state, let us see some of the example of the aqueous complexes of first order transition metal ion. We have various aqueous solution of titanium 3 plus, chromium 3 plus, manganese, iron, cobalt, nickel and copper solution. You can see a varieties of color possessed by this metal ion in the solution state as well. So, what is the science behind the color in the solid as well as in the solution state? In the earlier lecture, you have also learned about the variable oxidation state possessed by the transition metal ion and their compounds. You have learned that manganese can have oxidation state ranging from +2 to +7. Vanadium and chromium are also the other example possessing a variable oxidation state, and the different color are associated with different oxidation state at different pH. The question comes that why they are having different color. One more example, in this case we have a vanadium and chromium complexes having different ligand and different charge on the metal ion. In the first case we have a vanadium in 2 plus oxidation state, in the second case vanadium is in 3 plus oxidation state. Although the ligand in both the cases is same, that is water or aqueous complex, but the resultant solution is in different color. In the another example, we have a two solids having one having 6 amino ligand. If you replace one of the amino ligand by chloro ligand, the resultant formation of a complex is forming a altogether different color compound. So, what makes the change in the color with the change in the oxidation state and also with the change in the ligand identity. So, one more example we have here, some of the d block metal ion in the aqueous solution. We have a copper, cobalt, zinc and iron in aqueous solution. We have also some of the salts of copper, iron and manganese in the solution state. So, why they are colored? What is the science behind the color possessed by the compound or the complexes of transition metal ion in the solid as well as in the solution state? To understand this, let us first understand why any object looks colored. We see the colored object because light striking on them. Suppose if I am giving this lecture in a dark room, then you will be not able to see me. You are able to see me because when some of the light falls on me, some of the light will get reflected back and therefore you can see me. Same is happening with any object. When white light passes through any object or in solution, then some of them will be absorbed by them and some will be reflected or transmitted back to the object. If the wavelength absorbed are in the visible part of the spectrum, then solution will be appearing colored, and if a solution appears purple, suppose for example, then it is absorbing a light in the green and yellow region in the visible light, and therefore it will appear purple. And the other wavelength of light, it allowed to pass through it. So, why most of the transition metal compounds are colored? Transition metal have colored ion because the d energy level are close enough together to allow visible light to excite electron and therefore forms a lower to a higher level. But still the theory is not very simple. The color depends on the presence of partially filled d cell, and that is why transition metal have typical color. Copper is blue, iron is green and Fe is yellow because of all have a partially filled d orbital, and there is a chances of an electron to raise from one d orbital to another d orbital. A solution of copper sulphate is blue because when a white light falls into it, red and yellow wavelength is absorbed by it, and it will transmit the blue color light to the object, or when we see it, it looks blue in color. You are also aware that the visible region is in the range of 400 nanometer to 800 nanometer, in which the 400 nanometer or 4000 angstrom light corresponds to blue light, and the light having 7000 to 8000 angstrom or 700 to 800 nanometer is red in color. So, here is the artist wheel, in which there is a relation shown that how which color light is absorbed by the molecule or the solution, and what will be the colored appear by it. Say for example, if compound or the solution is absorbing the light in the red color region, that is to say in the wavelength region of around 630 to 750, then the color appeared or the color of that compound or the solution will be green in color, because red is complementary to the green, and therefore, the compound which absorb the red color light will appears green. And similarly, if the compound absorbs blue color light, it will look orange in color, because blue and orange are complementary to each other. The same thing is tried to shown by this table, in which the absorbed light and the observed color of an compound is shown by the complementary color. As I said, if the compound is absorbing somewhere in the yellow region having wavelength 580 nanometer, then the color of that compound or the solution will appear dark blue, that is 430 nanometer. So, this is how the color observed and color absorbed is complementary to each other. So, in this complex, this cobalt complex is orange yellow, or one of the another cobalt complex is purple in color. Why it is orange yellow and why the other is purple? Again, the answer lies in this artist wheel, wherein we have the relation between the absorbed light and the observed light. A substance absorbs visible light of a certain wavelength. As I said, it reflects or transmits visible light of other wavelength, that is, it is complementary color, and therefore, it will be appeared color. So, here example of a tetra-aquo copper complex which absorbs yellow color light and it appears blue in color. Similarly, if tetrachloro copper complex we have, it absorbs blue color light and it looks or it appears yellow color, because blue and yellow are complementary to each other. The question is, what happens exactly when the different color light is absorbed or transmitted by the compound of transition metal ion? To understand the answer of this question, we have to understand the shapes of d orbital and the changes in the energy of the d orbital under the influence of various ligand. As you are aware, there are 5 d orbital having lobes lying either on the axis or in between the axis. We have d x square minus y square and d z square, and we also have d x y, d y z and d z x orbital. In this, 3 orbital is having the lobes in between the axis, while 2 of them having lobes on the axis. And depending upon this, initially in the gaseous state or when there is a no ligand, all the 5 d orbital are equal in energy, or they are called as degenerate orbital. But when ligand comes, it perturbs or changes the degeneracy of the orbital, and the 5 degenerate d orbital splits into two group, namely Eg and T2g. And therefore, what happen? If electron is associated with the lower energy d orbital, then it may jump from lower energy d orbital to the higher energy d orbital, and therefore, this will be called d-d transition. Since electron is jumping from lower energy d orbital to higher energy d orbital, the transition is called d-d transition. So, this is a repetition of what I have told you, that initially the d orbital are degenerate, that is to say they are of equal energy, but under the influence of ligand the degeneracy is perturbed or lifted and resultant into two groups. Same we can understand pictorially. This is how the degeneracy is removed, and we have a two groups, namely Eg and T2g. Eg is the higher energy orbital, in which we have a 2, namely dx square minus y square and dz square, and the lower energy group of orbital, 3 orbital in this, namely dxy, dyz and dzx orbital. Of course, this will be the case when there will be 6 ligand surrounding the metal ion, forming an octahedral compound. The story will be different if the number of ligand either changes or the geometry around the metal ion changes. In octahedral, the d orbital splits into Eg and T2g. In tetrahedral, it will be T2g or Eg, or in square planar it will be still different. The more on the crystal field splitting and the science behind it, you will be learning in different unit. But the question is, what is the criteria for this d-d transition? Can we have d-d transition in all transition metal ion? No. It requires to have unpaired d electron in the transition metal atom or ion. If transition metal atom or ion do not possess any unpaired d electron, then d-d transition is not possible in such metal ion. The example includes, we have already seen in the beginning, is in case of a scandium, wherein we have 3d0, no unpaired electron is possible, and therefore, no d-d transition in case of a scandium 3 plus. Moreover, you require to have presence of incompletely filled d subcell. If all the d orbital is filled with the electron, then also there is no chance of d-d transition. The example includes the example of zinc in 2 plus oxidation state, wherein all the d orbital is filled with the electron and we have a 3d10 electronic configuration, resultant into no d-d transition, and therefore, both this metal ion scandium 3 plus and zinc 2 plus is colorless, as we have seen in the beginning. However, if we have electronic configuration from 3d1 to 3d10, then in all these cases d-d transition is possible, and which gives a different color to this different transition metal ion. As we have seen, d-d transition is not possible in 3d0 and 3d10 arrangements. So, to account the color of hexa aquo titanium 3 plus complexes, you can very easily say that titanium is in 3 plus. So, we have a 1 unpaired electron. Now, what happened? This 1 unpaired electron is occupying the lower energy T2g orbital, and when it absorbs the visible light, it will jump from lower energy T2g to higher energy Eg, and during that it absorbs certain energy, and when it comes back it emits certain transmitted light, and that transmitted light will be the color of actual titanium hexa aquo complex, and the color is purple color, and this is why hexa aquo titanium compound is appearing purple in color. Let us understand the one more example of d-d transition in cuprous or cupric ion Cu2 plus. Here also we have a 9 electron in Cu2 plus. So, this 1 electron is possible to have a d-d transition. So, here you can see that yellow light is absorbed by this, and the complementary color of a yellow is a blue, and therefore, all the cupric ion compound is appearing blue in color when water or H2O is acting as a ligand. Another example of DD transition is by Fe2 plus ion. Here also we have 5 total 6 electron, but the higher energy d orbital is vacant, and therefore, there is a chances of DD transition. So, one of the electron from lower energy orbital is promoted to the higher energy Eg orbital, and the Mangetta light is absorbed, and the complementary color of this Mangetta light is a green in color, and therefore, this Fe2 compound will be appearing green in color. Let us see the question of a zinc 2 plus. Here all the d orbital is filled with the electron. There is no vacant d orbital is there, and therefore, there is no DD transition is possible, and therefore, there will be no DD transition, and therefore, the compound of zinc 2 plus will be colorless. Similarly, in case of a scandium 3 plus, we have no electron, although we have all the vacant d orbital, but there is no electron available, and therefore, here also DD transition is not possible, and therefore, this compound will be colorless. Now, the question comes, the splitting of this d orbital into these two Eg and T2G group depends upon the nature of ligand. That is how this delta E changes with the change in the nature of the ligand. So, on what factor delta E depends? It magically depends on 3 factor. So, let us understand it one by one. The color of the transition metal complex, as I said, depends upon delta E, which in turn depend on the nature of the ligand. We have a chloro, fluoro, etc., which are very weak in weak nature, while amino, cyano, etc., are very strong ligand. So, when you have a ligand exchange reaction occurs, then the color of the compound or the complexes changes. Let us understand it by taking one example. We have a 2 copper complex, one aqua complex having water as a ligand, which is absorbing red color light, and therefore, it is appearing something like greenish in color. But when you replace from the coordination sphere 4 water molecule by 4 amino ligand and forming this type of a compound or complexes, then all of a sudden the color of the complexes changes from green to the blue, because the light absorbed by the earlier complex is red light, while the second complex absorbs the yellow light, and depending upon the complementary color, the color of this is changing. So, this is how by changing the type of ligand in given complexes, the color of the complexes changes. Let us take another example in which instead of changing the ligand, now let us change the oxidation state of metal ion. In the first example, we have a chromium complex having 2 plus oxidation state, while in second example, we have a chromium in 3 plus oxidation state. Both are of course an aqua complex having same ligand, that is water molecule. But now, with the change in the oxidation state also, color of the complexes or the solution changes. So, we can say that the color is also depend not only on the nature of the ligand, but on the oxidation state of the transition metal ion, and with the increase in the oxidation state, your delta E increases. The third factor of course is the coordination number. As I told you, the geometry around the metal ion is also a very important factor in deciding the color of the solution. Here we have a 2 cobalt complex. In the first cobalt complex, we have 6 water molecule attached to it, forming an octahedral complex, while in the second case we have a tetrahedral cobalt complex having only 4 chloro ligand. Now, as the geometry changes, you can see the color of the solution is also changes. Octahedral cobalt solution is pink in color, while the tetrahedral cobalt solution is blue in color, and therefore, we can say that color changes with the change in the coordination number of the complexes. So, here are some of the example of a copper complexes in which different ligand is there. In first case we have a water or aqua ligand, chloro, amino, ethylene diamine and EDTA. With the change in the ligand, you can see the notable difference in the color occurs, because the change in the ligand also changes the environment around the metal ion, and not only that, the ligand exchange reactions when occur, then you can see a different color of the complexes. As I said earlier, with the change in the oxidation state of the metal ion or change in the ligand also changes the color of the complexes. So, now with the change in the oxidation state, how color changes, already we have learned this when we have seen the variable oxidation state, but again to repeat it, let us see the different complexes having different oxidation state of vanadium ion, and thereby we can see a different color. One side question I would like to ask you here is, we have AgCl, AgBr and AgI, out of which AgCl is colorless, AgBr is pale yellow and AgI is yellow in color. In all these three, the silver is the metal ion and silver having no d electron. Still we have a AgI is yellow in color. Is dd transition is there in AgCl or AgBr or AgI? The answer of this question is of course no. There is no dd transition. So, other than dd transition, there may be another factor which plays an important role as far as the color of the transition metal ion is concerned, and that factor is polarization. In this, Ag polarizes the halide ion, that is chloro-bromo or iodo. In all these three cases, silver ion is polarizing the halide ion, but the polarizability of iodide ion or iodo is more, that of bromo or bromide ion is intermediate and that of chloro is least, and because of that, depending upon the polarizability of the halide ion, we have a different color of this compound. Some of the silver compound like silver carbonate is yellow in color, or silver oxide or silver sulphide is black in color. This also can be explained on the basis of polarization phenomenon. That is to say, in this case also the anion is being polarized by the cation. So, we have, depending upon the polarizability of the anion, we will have a different color of the compound. Now, let me ask you one question about the color of the chromate, dichromate or permanganate ion. You have seen the potassium dichromate, potassium chromate and potassium permanganate salts. They are very intense in color. Potassium chromate is strong yellow color, dichromate is orange in color, while potassium permanganate is intense purple in color. If you calculate the oxidation state of the metal ion in these salts, then you will come to know that in either chromate or dichromate, the chromium is in +6 oxidation state, while in permanganate, manganese is in +7 oxidation state. Chromium in +6 or manganese in +7 oxidation state possess no d electron, and therefore, there is no dd transition is possible in all these cases. Although we have an intense color in this compound. In the absence of dd transition, what is the other phenomenon which giving the color in this case? To understand this, let us understand the charge transfer phenomenon. In the all these three cases, what happens? There is a momentarily transfer of a charge from oxygen to the metal ion occurs, and therefore, momentarily O2 minus changes to O minus, reducing the metal from +7 oxidation state to +6 oxidation state. And because of this, due to this charge transfer phenomenon, we have a color associated with these anions. So, potassium permanganate or potassium chromate or potassium dichromate all are colored due to charge transfer phenomenon. So, therefore, we have now 3 reasons for the color in the transition metal compound or complexes in solid as well as in the solution. These 3 are DD transition, or we have a polarization, or finally charge transfer transition. In this slide, I have tried to show you the different color with possessed by the transition metal ion of first row series with different oxidation state. You can see that how color changes with the change in the oxidation state of the transition metal ion. In this lecture, I have introduced to you about the phenomenon associated with the color in transition metal in solid as well as in the solution state. We have also learned about the DD transition, about the polarization phenomenon and about the charge transfer phenomenon occurring in these complexes. With this, we come to an end of this unit, in which we have learned the important chemistry of first row transition metal ion in this series of lectures. In the next lectures, I will going to tell you something more about the second and third row transition metal ion.